We're going to continue with another problem. This time we have a cart right here attached to a mass over a pulley. We'll know the mass of the cart and the mass of this second object hung over the edge of the pulley. We will again assume the pulley is light and frictionless and that the string is light and will not stretch. We'll take the surfaces to be frictionless and also to be level, and we'll take the string right here to be parallel to the surface. What we're going to look for is the acceleration of each of the mass 1 and mass 2, and we'll find the tension in the rope. And we will solve this problem exactly as we'd have before with the same procedure. So first we're going to draw the free body diagram. So what I want you to do is, in your notes, take a sketch of the free body diagram before we continue. Okay, drawing the free body diagram. Well, notice we're told there's no friction, so we don't need to worry about frictional forces. And again, we're going to assume no air resistance because we're not given enough information to calculate it. And again, something like this, the velocities will be small enough we can neglect them. We will have weight for both the cart and the mass hanging off the end. Again, note one will be m1g, the other one m2g. We do have a normal force right here on the cart, which will counterbalance its weight. And we do have a tension force acting on both the cart, pulling it forward, and the block on the end, pulling it upwards. And those are our forces. So there's the free body diagram. Next, we need to pick our inertial frame of reference. Here, because the cart will be moving horizontally and the block will be moving vertically, it makes sense to make our axes horizontal and vertical. Notice all of our forces are either horizontal or vertical, so we don't need to worry about breaking any vectors into components. The cart will be accelerating only in the x direction, and the block will only be accelerating in the y direction. So that will basically simplify the math. And again, the frame of reference must be attached to the ground so that it is an inertial frame of reference. Our next step is to take and apply F equals ma to both of the objects, both the cart and this little blue block hanging off the end. So take a moment and write down F equals ma for both of these, both the x and the y direction. Okay, hopefully you've done that in your notes. So now let's take a look at them. For the cart, mass number 1, we add up all the forces acting in the x direction. Well, that's only the tension, and it is acting in the positive x direction, so it's T equals the mass of the cart, m1, times its acceleration, a1. Vertically, we just have the normal force and the weight, and they must add up to 0 so that the cart doesn't fall nor hop up. Mass number 2, we have the tension up and gravity down, so T minus m2g equals m2a2. There are no horizontal forces, so there's nothing there. Next, we'll apply our constraint laws. We're using our sign convention, which means A1 will be positive to the right, and A2 will be negative if going down. And the cart must be moving to the right for the positive acceleration, and the block must be moving down with a negative acceleration. So long as the string doesn't stretch, for every centimeter that the cart moves to the right, the block must move down a centimeter in the same amount of time, which means the velocities of these two must be equal in magnitude, which means their accelerations must also be equal in magnitude, just like it was in the Atwood's machine. And given our sign convention, they must be opposite in sign. So A1 must equal minus A2. And again, like in the Atwood's machine, we're assuming our pulley is light and frictionless, so there's basically nothing between one end of the string attached to the cart and the other end of the string attached to the block. So therefore, the tensions on either side must be equal, which is why we haven't bothered to distinguish them. Now that we have identified all of our equations, let's collect them all together. So we have the tension equals m1, and I'm just going to call that A because we're going to call the acceleration a1 to be A. And tension minus m2g equals minus m2a. And that gives me two equations and two unknowns. So what I want you to do is take a moment and in your notes solve those two equations for the acceleration A and the tension T. Okay, the solution you should have gotten is the acceleration is m2 divided by the sum of the masses times g, And the tension is the product of the masses divided by the sum of the masses times g. Now, let's make sure these make sense. First, we should make sure that these expressions have the correct units. Does A have the acceleration of acceleration, and does T have the acceleration of force? Well, looking at this is a mass divided by a mass. The kilograms right here will cancel out, so A, in fact, will have the same units as G, which means it'll have the units of acceleration. Tension will have the units of kilograms times kilograms divided by kilograms, so that will give me kilograms times G, which is a unit of force. So we do, in fact, have the correct units for our two expressions. Now, to double check them a little bit more, let's take some extreme cases. What if M2, the block hanging off the end, is very, very heavy compared to the weight of the cart? That means, in that case, the block should essentially just be in free fall and the tension should go to 0 because it's not being restrained by anything. So if we take M2 and make it very, very big, adding M1 down here on the bottom essentially won't do anything. So this fraction will essentially be M2 divided by M2, which will cancel out. The acceleration will approach g. The tension, again, here we'll have M2 plus a very small number, so that'll essentially be M2. These two M2s again will cancel out, and the tension will be the small M1 times g, which will be a very small number, or the tension will be very small. So that, again, checks out. What if we have the reverse? And M1, the cart, is very, very heavy, and we're just hanging a very small mass on the end. Then we'd expect the cart to do nothing and to stay at rest and to not accelerate. And the tension will just equal the weight of the hanging mass because the hanging mass won't be moving. So let's make M1 very large. Well, if M1 is very large, essentially we have a small number divided by a big number, so the acceleration will go to 0. Now here we're going to have M1 be very big. Adding M2 will be negligible, so the bottom will essentially be M1. We have M1 on the top, those two will cancel out. The tension will just equal the weight of the hanging mass, which will be sufficient to keep it from moving. So again, the answer makes sense. It passes these two tests. So we're done.